I'd like to take us from 40,000 feet down to 4 feet, down the protocol stack from security down to the physical layer. So I would like to talk to you today about our work in optical code division, multiple access testbed, and also in microsystems to move that testbed into small devices that can be used and distributed at modest cost, we hope. The PI on this project is Professor Ben Yu, who is today, along with several of our students, unfortunately at our major conference in Los Angeles, the Optical Fibers Conference. I gave my talk down there Monday and rushed back up here to talk to you folks. The other faculty members involved are listed here in various projects. I won't mention all of their names. We're also a collaboration with Lawrence Livermore, Rebecca Welty. And I want to say something too that I'm going to concentrate on. I'm a task leader on the optical test bed, and my discussion today will be concentrated on that, but we have several posters where a couple of students are here, and also a postdoc here who have posters on sort of the device, indium phosphide devices that are being built in this project. So, well, CDMA, code division multiple access, that's something which has been around for a long time. Traditionally, it's been thought of as being used as a modulation of a bit in the time domain at a rate much faster than the bit length, modulating it into a sequence of smaller units called chips. That modulation might be a pseudo-random sequence, specially chosen, or perhaps even hopefully for encryption. And the result of that modulation, of course, is it spreads the spectrum of the pulse. So it's a process that originated from original ideas in spread spectrum communications. It has seen applications in military and also recently, of course, in wireless. By encoding in this manner, one can help avoid interference, and there are certain other benefits that accrue in a wireless environment. But the question is does it make sense at all, or what benefit could be derived from using CDMA principles in an optical fiber optic environment or a free space optical environment? And I don't think there's a good clear answer for that yet, but the one thing that we think about and are trying to exploit is, one thing that you can imagine this doing is that each bit, you could view this modulation as is carrying its own address, right? And therefore, you could then send onto a network in a kind of a very low protocol way, just drop your stream of information with the bits carrying the address, and then let at the physical layer a conjugate mask, which I'll explain in a moment, reject all of the other users that are on the network and only accept the one where the target address matches up. And that's the general idea. This could be potentially useful in a network that has to be reconfigured rapidly a lot. For example, a network maybe in, say, an aircraft or in a ship or something where systems are changing, or in, of course, a sensor network potentially, or in environmental studies. So presumably then one could try to take advantage of ease of provisioning because of the low protocol overhead on this process. Also, some people, this is a DARPA-funded project, by the way. There are 5 other groups funded to solve various aspects. Some people are actually looking at encryption. Our project is not, although what we're doing is not encrypting for sure. But there is an element of data hiding that may accrue from this. For example, we're taking very broad spectrum, low energy pulses, spreading them out in time. Those could be, in fact, dumped right onto a WDM system, taking up all the space that's unused in the WDM, and the encoding rejects the WDM. So, you could drop an additional network onto a fully laden WDM system, for example. And so that's sort of this utilization of unused spectrum. Well, what about our project? Our project has 2 really big main aspects on it. One is a testbed evaluation of these concepts using a particular concept I'll describe to you using free space optics. I'll show you this, and it takes up a lot of space, by the way, and optical space and physical space, and also then moving towards an integration of these concepts down onto chips, to make a 1,000-fold reduction in the size of this down onto chips the size of your thumbnail. So we're in the first year of this project, and our testbed evaluation is up and running, and we're meeting our first objectives and goals. So what we're doing is an OCDMA technology assessment. We have to test coding and decoding, and do we need to use forward error correction to achieve good bit error rates? We're looking for bit error rate and multi-user interference measurements, and I'm going to show you those measurements that are successful. Now, what about the approach? How does one do CDMA in optical domain? Well, there are a lot of different ways of doing it. One could think of just mapping the electronic method right into the domain, but if you do that, you're ignoring the fact that you have available to you an awful lot of bandwidth in optical short pulses that can be made. And so the approach is to try to take advantage of that enormous bandwidth. It's easy in optical business to make half picosecond long optical pulses with terahertz bandwidth available. So how can we make use of that bandwidth in a network environment? I mean, we're not going to necessarily transmit information at that bandwidth at that rate, but how can we use it? And so what we're doing is we introduce this approach which we call SPECS, which is spectral phase encoded time spread optical CDMA. So we start with a short optical pulse. We modulate in the spectral domain and thereby spread in the time domain. So it's kind of the Fourier transform of the spread spectrum approach. We have demonstrated now a tabletop bulk optical testbed setup with 4 users working in this to show the basic principles. So let me go on and explain this a little bit more, how this works. The SPECS is based on an optical device which actually a colleague of mine and I invented back when I was in my Bell Labs and Bell Core days. It consists of a pair of gratings, a pair of lenses in a particular configuration where everything is spaced by a focal length of the lens here. And then in a special spot in the configuration, we introduce a spatial light modulator, which can modulate the phase or amplitude of the spectral components. So what happens here is as a short pulse comes in, the various colors are dispersed by the grating. They're then focused by this lens to a sharp line along this path. And then so, for example, at this point, these blue components can pass through a liquid crystal filter that's addressable electrically, not unlike what's on the screens of your computers, and shift the phase of that component relative to others. So here we can now spatially introduce a modulation, right, and thereby on that particular bit stream that's going through, spread the timeout. This modulation in the spectrum takes that short pulse and spreads it out long. And if this is a pseudo-random sequence, it even has a very noise-like character look to it in the time domain. Then what's neat about this and what's sort of magic about this is you can put all of those components back together and then have this broadened out and reshaped pulse over here. And it's done in a way, this is not a trivial matter because, by the way, the fact that all these colors are going off in the different directions means that there's dispersion in the group velocity from here up to this point. But the mirror symmetry in this puts everything back together again so that there's no frequency-dependent phase imposed in here other than what you're putting in on that device. So what we do is we'll encode our pulses here. Put an address on each bit, if you will. So to give you a physical picture of how you encode and then decode, let's just imagine that I have my short pulse coming in here on the left, and then right up here, let's suppose the wavelength is spread in this manner. So I could make a little phase mask, and here's one. This is a piece of glass, with this relief etched into it, right? So the components at this frequency suffer a larger phase shift than, say, at the one adjacent to it where it passes a shorter distance. Well, if after passing through the transmission media and then being spread out again, we have, a conjugate phase mask here, which is what this is, right? Then, of course, there's no net phase change for all of the components through this, right? You can push that together onto that, and they match, and it's just passing through a piece of glass. So that means that we receive a short pulse out. Here, suppose we now have chosen a different, let's call them a lock and a key, right? A different key, and we choose these codes in such a way that this one, when multiplied by this conjugate one over here, still produces another broadly spread pulse. I mean, actually, right out of here, the pulse is spread widely too, but of course that reconstructs the pulse. So we're sending around all these noise-like bursts with low intensity, right, randomly produced on the network, and then filtering and extracting the one we want here. How? Because we have to distinguish and threshold between this high-intensity pulse that's short and this low-intensity pulse that's long, or a sequence of those if there are multiple users. That's a challenge, by the way, because the time frames we're talking about here are short. These pulses may be broadened out only into the 40 picosecond regime, and typical photodetection means we're integrating energy. And photodetector will see the same energy in that as that. So what we do is we do some nonlinear thresholding, optical nonlinear thresholding, the nonlinear intensity-dependent response on the short intense pulse being stronger than on even the sum of all these others. So that's the basic idea. And so what we'll do is we would have an encoder like this, and spread pulse come out, and it goes to some kind of a network, and then a decoder in this fashion. Now, how can we make sense out of this? You can see this is a big thing, physically a large thing. Our project, as we move down on the project, is to move to a planar implementation of this in indium phosphide, and that shows how that works down here. What we'll do is we fabricate on a substrate an arrayed waveguide grading device. Right, this device right here, which consists of a region where the wavelengths are allowed to spread out, and a region which is guided in the vertical dimension but allowed to spread in the horizontal. All components propagate along these arrays of different path length, and then at the output end, only certain wavelengths match and interfere constructively to give you an output onto a particular path. So this is a grading. This is equivalent to this right here. And then we can introduce on the substrate modulators and then put them back together again. And so this is in fact being constructed right now, and we're moving forward to implementing these bulk optic devices on the planar substrates. And this is what the posters that I'd like you to visit outside. I'm going to go back and talk about this work. It's what we're doing is building 4 channels. Basically, it means 4 transmitting channels, and that requires 5 encoders and decoders, one to be used as a receiver to decode. And one of the ways that we do that to keep the costs reasonable, instead of having a lot of these liquid crystal spatial light modulators, is we have one 2-dimensional one. And this is kind of a little schematic of how the light pulse comes out, sent through optical circulators, through fiber collimators, and then we have 4, in this picture, planes on this reflection mode liquid crystal spatial light modulator. That's what that stands for. The individual channels are brought back through the circulators and out. Sorry, here was I did it backwards. That's the transmitter, and there's the receiving end. And then a decoder, which consists basically of just one of those in a 1-dimensional device. Let me show you a little bit about what the actual measurement that we use. We start with a short pulse fiber laser, which consists of a clock and a pulse compressor and an amplifier to produce about a half a picosecond pulse. Runs at 10 gigabits per second. So we'll be doing measurements up to that rate. The beam is then, after polarization control, modulated by pseudorandom sequence from a bit error rate test set. After some amplification, the beam is split into 4 channels, and the 4 channels are shown here. The 4 channels are shown here, and with the beams propagating down to that 2D encoder I showed you, right? And we also send one to a 1D encoder. So this one is going to act as our transmitter, and all of these are going to be other users which we'll view as interferers that we want to reject. By the way, these optical delays are put in, are sufficient so that the single modulation, since it's a pseudorandom sequence, we move as many bits in sequence, so then each channel has its own pseudorandom sequence. That, of course, saves money again because these modulators are expensive. These fine delays allow us to tune into a synchronism all the pulses so that we can test in sort of the worst case situation or move out into random times. Of course, all of the signals are treated equally. Attenuators are there so that all the powers are leveled. Then we amplify it through a transmission link. At the moment, the transmission link is only a few meters of fiber as we're demonstrating the principles, but with dispersion compensation, we expect to be able to go a kilometer kind of distances. And then here's our decoder, which now, of course, is going to allow this bit to pass while rejecting all of those others. Let me show you. Now, after having done that, we have to extract that information, because here what we have is, and I'll show you this in a moment, a short pulse riding on the background of a lot of noise. This is the key in this whole operation, is this thresholder, this nonlinear thresholder. This is the most important element in it and all, right? What we use is a highly nonlinear fiber. The intensity-dependent refractive index broadens the spectrum when the intensity is high. The long-pass filter passes that and rejects the low-intensity interferers. This is it. I mean, we may want to go to gating on this to improve performance. But at the moment, there's no gating at all other than what's provided by the nonlinearity. Timing is not, at this point, required. The output of that, of course, then goes to a standard 10 gigabit receiver and then to the bit error rate test set not shown. Let's see what we have now. So this shows you the spectrum coming out of that nonlinear thresholder, right? Just to show you, to clarify the point that I just made. The red line is the spectrum generated by 3 interferers running simultaneously, all with the same average power. All right. The blue line is the signal coming from the decoded short pulse. All right. And so this dotted line right here is the long pass filter showing that all of this stuff over here is rejected, and this is what's transmitted. And so our normal now electronic thresholder now only needs to distinguish between the energy under here and then reject that little bit of energy down here. So let me just show you to emphasize this is a big project. Here are the gratings for an encoder. Here are the commercially available 1D spatial light modulators were actually made for this pulse shaping process that we're using and commercially available. The gratings, this is a 2-meter long operation. This is only half of it. Right, that's the decoder and one of the transmitters, and over here here's the 2-dimensional spatial light modulator. It's grating, right? Cylindrical lenses that we required. Thresholder is way down over in here, and then here's the bit error rate test set. So it takes up a substantial chunk of a good-sized optics laboratory. So one of the objectives, of course, in this project is to bring that down to something small. Well, what about our results? Well, what I'd like to do here is show you what is actually, this is a measurement. This is what's called a cross-correlation measurement. We actually can measure the short optical pulses. They're in this half picosecond range. This is about a half picosecond correctly decoded pulse from the user 1, right? And here is the interference coming from all of the rejected or to be rejected users. So this is after the passive decoder, but before going into the nonlinear device. The nonlinear device then, of course, has to distinguish between this and this. And, of course, the area under here is actually larger than the area there, but the nonlinearity is what allows us, because it's intensity dependent, allows us to pick that out. This is a bit of a challenge. It really is, because all of those optical fields are interfering, right? And so there's a random phase that pops up when all those pulses are arriving at the same time. And sometimes they'll add constructively, sometimes destructively. That actually has the effect of building the signal strength up or reducing it. And so the eye diagrams actually wiggle up and down, which they don't normally do in a regular communications channel. Nonetheless, we've been able to actually demonstrate error-free performance at 10 gigabits for 4 simultaneous users using this principle. This is actually the first time this has been done, although OCDMA in this style has been worked on off and on for the last about 10 years. Let me show you some things here. This is basically the back-to-back measurement. We're just sending one signal through the encoder-decoder, and then giving the easy task to the nonlinear thresholder to detect. Here we are with one user. There's a power penalty. Oh, excuse me, we didn't have the encoder and decoder in here. That's the power penalty associated with that. Then as we add users, right, more power, the curves shift to the right. So here is the one user, the signal channel. Here is the signal channel plus 1 interferer. Here's the signal channel plus 2 interferers and 3 interferers. All right, and so this progression to the right is a little bit unusual, but it's understandable in this case because each time we bring in another user, we're adding an equal amount of power, right? And what I have measured down here is the total received power, all right, going into the thresholder. All right, so they march to the right. The fact that they're not perfectly uniformly spaced comes about from the different codes that we've chosen. Some are slightly better at rejected by the conjugate mask than others, so it's not perfectly uniform. You can see over here the eye diagrams. This is a return to zero eye diagram for the back-to-back case, which is very, very clean. And as you move up into this high region, the four users, you see the eye, while it still is clear and open, has collapsed a bit. Nonetheless, at this power level, right here, this arrow means that at this particular power where that points, we were able to sit for 5 minutes at 10 gigabits per second, which means that it's below 10 to the minus 12 bit error rate. Very good. So this is a very encouraging result, but there is still a lot of work to be done in improving this, and we have a project involved. By the way, I can also show you results at 1 1/4 gigabits, which we had done earlier. One thing that, I apologize for the somewhat messy picture, but one thing that one point I wanted to emphasize is that we start with a rather short pulse, and if the time from here to the next pulse is at 10 gigabits is so long as 100 picoseconds, we start with this half picosecond pulse and maybe spread it out to a few picoseconds, so that's sort of represented here and here. So we're really not even using potentially a lot of this time space in between. So one can improve the capacity of this in two ways which we're looking at. One is to use a slotted OCDMA, where we say let's give up a little bit of the flexibility of completely randomly dropping things in asynchronously, and let's move some of them into different time slots. Or let's be careful and see what we can do by just randomly dropping them into it. So there's always now the issue of synchronous measurements and asynchronous and slotted and not slotted, and those are areas in which we are studying right now. Of course, the measurement I showed you is synchronous. We also have a project on measurements, and sort of the bad news is, in doing the calculations, is that a purely asynchronous simulation show that and calculations show that purely asynchronous transmission is not as favorable as you'd like it to be. I showed you synchronous results where it was quite good. The bit error rate is nowhere near as favorable. Here it's shown, for example, for a long M sequence as at its best. It's at this point where we'd like to bring in forward error correction to help bring things down. And we're working on a high-speed forward error correction. The synchronous case is quite a bit better. Synchronous errors, let me just show you that doing a synchronous 31M code, so here's the bit error rate against the potential number of users. We're down here at 4, right? Way down there, error-free. But it's considerably better here in a synchronous case. But not only that, we can even do better by tailoring our codes a little bit. Simulations show that, and in particular, because our spectrum is not rectangular, gap has some spectral shape to it. If we weight our chips according to that spectrum to get the energy codes up, then we actually expect even a bit more improved performance. And so we're working on these codes tailored to our particular application. This is where we're heading. This is Professor Yu's main project. And again, I'd like you to take a look at this. Putting onto a chip, a small, actually it's not a ring laser we've come to now, but a linear laser on chip. The encoders through the AWGs, the modulators, and then a similar thing for a receiver at the other end. And then the detector would not be that nonlinear fiber detector, but rather an asymmetric Mach-Zehnder interferometer with optical semiconductor amplifiers providing the nonlinearity. Again, go to the poster session and we can talk about the details of how that works. That's where we're heading. What have we done so far? This is, of course, done in indium phosphide for 1.55 microns. All the work was at 1.55 microns. Here shows a prototype of a Mach-Zehnder, an AWG. Here are the modulators, right, bringing them back into another AWG. And it's also been wire bonded to drive the modulators. And also working on packaging of these devices. Here shows that device packaged in an optical package, and then also an electronic packaging as well, and for cooling. So work is continuing on that, and that's further down in the next several years on this funded project. So I guess finally I just wanted to say that we've demonstrated this 10 gigabit 4-user error-free performance with an optical CDMA. Our simulations provide a roadmap for expansion of the user numbers. We do need work in that area. We're working on the fabrication of indium phosphide-based encoder-decoder components and on on-chip lasers. And of course, the project also has a network simulator and study of protocols, which I have not had time to discuss. Thank you.
Since there's a poster on this topic, I'm going to defer questions until then so that we can try and get
Sorry,
back
I
on
went over a
screen.
minute
That's
or
all
two.
right. It's all right. We have a little